How's it going, everybody? I'd like to welcome you back to our next section where we talk about how to explain IP operations. And it's not a very complicated topic, but there's a lot of specifics to the IP protocol that I feel need to be addressed and figured out before you can really dive into any other topics because of the fact of what they mean at a fundamental level. Now, I've read Routing TCP/IP version volume 1 and parts of volume 2 obviously for the fundamental understanding of it, but more importantly to figure out why things work the way that they do. Because ultimately that's what a CCIE does. They really know how this stuff works. So what I've decided to do is decided to make sure that when I'm doing my demonstrations and talking, I always leave up the RFC link up here in case you guys want to go check it out. I copied this right from the RFC website because of the fact that I felt like it would be beneficial. And then I started doing a little bit more digging and I found the type and codes breakdown, and basically to explain how things work the way that they work. So I'm going to take a few minutes here and explain to you and draw out a quick demonstration as to how Icp unreachables and redirects actually work and why they do what they do. So a destination unreachable is generated by the host or its inbound gateway to inform the client that the destination is unreachable. So if you get that, that means that it can't get to where it's got to go. Pretty straightforward, right? So a destination unreachable message may be generated as a result of a TCP or UDP or another ICMP transmission. So typically they respond with a reset to close out the session so that the TCP connection doesn't stay open and cause what they call an embryonic TCP session or a half open. Half open meaning the first part and the second part have taken place, but there's not been a third part. This part hasn't taken part yet. So that's the idea behind it, what that means. Now, assuming you have a connection like this, and this is actually right out of the book, and this is what we need to get to. So this is going to be the server, and we have a connection between this guy and this guy. This is the default gateway over here, and we have a connection down here to a user. Okay, so this user is on the .100 connection. DHCP gave him that IP address. This is the default gateway of .1. So when he sends traffic and going to this is .2, and this will be another subnet over here because routers segment broadcast domains. This will be the .100. So what ends up happening is this guy sends a message to the router and says, "Hey, I want to get to here." Well, what the router will do is the router will send a response back to the host, to the sender, and say, "Hey, I'm not the best way to get there. I'm going to send you over to here, and that's how you're going to get there from now on." So what will end up happening is they'll send a redirect message to the host, to the sending host, and he will be redirected all his traffic over here, even though his default gateway is over here. He'll send that information up here, and then as long as he's sending back and forth to here, that'll be exactly how the redirect works. It's that simple. Now, the same thing works at layer 2. Or if you have a redirect and you're trying to get to a place and the direction is being sent over here, when you're actually trying to get over here because of the fact that the MAC address works the way that it does. So, let's say you have another switch over here. And you have another switch over here. Well, the idea and premise behind the layer 2 redirect is pretty much the exact same thing. So what will end up happening is you'll get, and this is pretty typical of what they call Proxy Arp, which you'll get, and I don't know if you've seen this before, but I did a Wireshark capture just a few days ago at work to try to figure out a problem, and I was noticing a lot of retransmissions at layer 2. And I couldn't figure out why. I did a little bit of Googling, and I realized that because the fact, it's actually the layer 2 version of this right here, to where you have this guy sends to here, this guy tells you to go up this direction. So the exact same concept applies, where you're trying to get from here. You got the host right here on this guy right here. He sends up here. This guy forwards him off to this because of the fact that we have the source MAC and the destination MAC. Well, basically what ends up happening is this guy tells the switch, if you receive traffic in, go ahead and forward it this way. And then the MAC address table is able to make adjustments as it needs to send traffic that direction. So it's a benefit to know how to do that, but at the same point in time, it can be kind of a burden sometimes, especially when you're trying to figure out why. So I want to talk to you now about the Icp codes that are out there. Now, a unreachable is going to be a type 3. Okay, that's a type 3. And there's several codes that go along with unreachables to figure out what's going on. So type 3 code 0 is going to be network. And then 1 is going to be a host, 2 is going to be a protocol. If you get a type 0, meaning you can't reach that network. If you get a type 3 code 1, you can't reach that host. You can get to the network, but you can't get to the host. Type 2 is a protocol. Could be a translation issue between, say, PIM with multicast to OSPF, something to that effect. 4 is a fragmentation. We'll talk about more of that when we get to TCP and UDP operations when we talk about fragmentation, but that's the idea behind that. Type 5 is a source routing, strict or loose, disabled with no IP source route. 6 to 8 is unknowns and errors. 11, 12, 14, and 15 are for quality of service, and 9, 10, and 13 are administratively prohibited, where you may have a port shutdown, or you might have an access list that's blocking a particular port. And I actually found this out just the other day when I was working on an NTP issue, which is Network Time Protocol. We'll talk about that when we get more into the services and whatnot. But I was getting a lot of responses. There was actually a Type 3 Code 9. And I kept on getting, I had to look it up, and it was administratively denied. And then as I did a trace route on that port, I realized that, and I was looking at the Wireshark captures at the exact same time that I was actually sending this traffic. That's when I realized that it was going on. I looked at the access list, and it was being denied by an ACL. So, lo and behold, good old ACLs. Alright, well, on to our IPv4 options. And this is going to be kind of lengthy because there is a lot of options that are out there. So what I'm going to talk about now is what the options are, and I've got several links here for you to reference in case you'd like to. And like I mentioned in all of my videos, if you'd like the OneNote document, I'm more than willing to send that to you via email, or I might even put it up in Dropbox and just put the link out there one day and for you guys to download it. But realize that when I do that, I will have to update it because there's a lot of information over. You guys can't see it, but there's a lot of information that I haven't filled out yet. I'm delivering this to you on a per section basis. So I'm network principles, and I'll tackle layer 2, and then I'll look at layer 3, and then once I get layer 3, that'll be a big section. Is VPN, infrastructure, security, and services, stuff like that. So anyway, back to this. So we have options, and the idea of the option is to put in extra parts in the IP header for you to be able to do different things. So let me actually scroll down here. Actually, it's actually written out here a little bit, and as you can see, there's quite a bit to it. I mean, if you really get down to the nitty gritty, it's going to be a lot of specifics to what's going on. So let me break it down like this. So the way that IPv4 options work is the IPv header. The internet header length is 4 bits. It tells whether there are IP options in the header. So options need to be 32 bits. They're known as words. So if an option isn't 32 bits long, additional padding is needed to make it 32 bits. Okay, so the idea behind this, and I recommend you go read, if you go look up on this, if you go to this one right here and you look at this one right here, if you go check these two out, this will give you a good breakdown of how it really works, because there's a lot of detail to this. So basically the options are just the characteristics to when you go, and actually I'll bring up a router to show you what this means. If you do this, and you do ping, and you hit enter, and you hit enter again, and you type in 10.1.1.1, and you hit enter, and then repeat count is 5, We're going to say yes. Datagram size is going to be 5. That's how big of a packet you're going to send. We'll say 150. Anything in brackets is default. And you're going to say timeout is going to be 5 seconds. And extended commands, yes. And source address, these are where the options come into play. Okay, so once you understand that, that's where the options come into play. That's what's going on. That's what makes this stuff very need to know. So as you can see, we have quite a few things that we can work with. So now, if we were to look at this through a protocol analyzer or Wireshark, we would see this stuff being utilized. So the way that this works, it's pretty straightforward. If option 5 is seen inside of the IPv4 header, then there are no header options. Okay, this is followed by a 20 byte IP header. If there's no options used, the IP header is going to be 20 bytes. Now you might wonder, how did you get to 20 bytes? Well, very simple. You have 4 bytes is going to be the IPv4 header, IPv4 address. Okay, so 32 bits is 4 bytes, right? Well, option 5 means there's nothing there. So you take that option number 5 times the number of bytes that are dedicated to that, which is 4 equals 20 bytes. That's how that works. So there could be up to 15 options listed, or I'm sorry, not options. There could be 15, which would be the indicator in the IP header. That would equal up to 60 bytes. So if you take 32 bits equals 4 bytes and multiply this by the IHL, I forget what IHL stands for, number found in the options field, then you would get the number of bytes in the header. Okay, so we take 5 times 4 equals 20. Same thing with 15 times 4 is 60. So the IP header starts with 20 bytes. The IPv4 options make this value larger. That's why if you were ever to look at the IPv4 header, you would see that it's variably lengthed depending on what's going on. And the demonstration I just showed you about how you were to go in there and add things in, like the extended pings and stuff like that, those are all options that you can add in. Now let's talk about options for a moment, and so you guys have an idea of what I'm talking about. The options field, you're going to have a type field, and it's actually a 3-section thing. And actually I have it laid out right here. All this right here, this first block. Try to draw a straight line. And it's harder to do than it looks. So this is going to be the type section right here. And I'll change my color for the next one. This one right here is going to be the option. So this section right here. This is the options. And then the option number, and I'll change my color again to blue. This is this field. Oop. We'll do this. This is the options. I'll tell you one thing, the pen pad has come in handy so many different times when I've been doing this. So, as you can see, this is going to be this color. This guy will be this color. And this guy will be this color. So, go back to this. So that's what we have for that. Now, the length is pretty straightforward. Oh, I'm sorry. I goofed that up for you guys. I can't believe I just did that. I just realized that I made a mistake. So this is the type. And there's 3 different breakdowns for it. And these are the breakdowns for it. Now, when you look at it, this is correct. Let me change this up a bit here. This is this, which is the length. And this is the data. I'm sorry about that. I apologize. So this guy right here, let's go back to black. Back to black is going to be this field. And this guy is going to be all of this stuff right here. So all of this stuff that I'm shining over right now, so you guys have an idea what I'm talking about. So the variable, the 12 bytes, stuff like that. So that's what that is. I apologize about being wrong. So as you're going through the type field, so what you're going to see is you're going to see copied fragments set to 1 or 0, and copy 0 1 is copied, 0 is not copied, 1 bit in size. So if it's turned on, then it's not copied. If it's 0, it's not copied. If it's a type 1, it is copied. So the options class, you're going to have 2 bits in size. 0 is control, 2 is debug. Again, if this isn't 100% clear what I'm talking about, and I'm sure it's not unless you've got a lot of experience dealing with this stuff, I would recommend Googling it as well, because I might not give you the best explanation. But then you have the option number is 5 bits in size. So that's actually how this information is broken down right here. Now we have the length field. Is 1 byte in size, indicates the size of the option. So sometimes it could be 18 bytes, sometimes it could be 7 bytes, just depends on what's going on. The data that is sent with the option. So basically, at the end of the day, this guy indicates that there's something going on. This guy indicates that this is the length, and this is the one that says how big it's going to be. All of this indicates right here, is a feature turned on or off? And if so, if it's turned on, what do I need to do in the IP header? What do I need to be looking for? So when we look at it, as you can see right here, we have an enhanced version of traceroute. So if we have 2 turned on, 18 is going to be the length of the size, which if you were to do this, this means you're going to use enhanced traceroute, and then you're going to use, because the fact that the IP header can only hold 9 32-bit IP addresses from each router that the traceroute was passed through, then that means that you're going to have up to 36 bytes that it can possibly take up. Times 4 equals up to 36 bytes that it can take up in order for you to use a traceroute. This is what they call a record option. By using that, you're going to record every hop. So it's going to be from here to 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 here. So we got 1, 2, 3, 4, 5, 6, 7, and well, technically you could just add in a couple more here to get your 9. So you could go up to 9 hops. So theoretically, if we were doing asymmetric routing, that would be efficient. But if you were to do 1, 2, 3, 4, 5, 6, 7 on the return trip. Okay, so that's the idea behind that. It's pretty straightforward, but as long as you understand the concept of what the options field is there for, that'll be a great place for you to start. Now, we talk a bit about extension headers. How did that get all goofy? So, what'll end up happening is, interesting. Okay. The IPv6 extension header, it's a little simpler, where when you're looking at it, you're going to see it's a simpler, simplified compared to the IPv4 header. It's fixed in size, and it's 40 bytes in size. Okay. Now, when you're looking, if you were to pull up a Wireshark capture, what you would see is you would see the options, and I'm going to draw this out real quick. This would be the IP options field. So IP options. And what you're actually going to see is you'll see an indicator in Wireshark that this is turned on. Okay, so maybe potentially a 1. But what you'll see is you'll see the IP options, and this will be, just bring it out here a little bit for you. What you'll see is you'll see this, and you'll see whatever the option is here, and then what you're going to see is you're going to see a next header, which will indicate there's another option down here. And it'll keep going until this is filled out, and then this will keep going on. And next header. Eventually it'll go down to the last option in use, and then what you'll see is you'll go to the upper layer, which will indicate that it's going to stop doing options and it's going to start to go up the OSI model until the upper layer flag is seen to go up the OSI model. These will delineate all the possible options that may be used, which will basically just tell you that there's no more options for the router to try to add into the IPv4 header during transit. So that's the idea behind it. So the next header is what's going to be used. Oh, that's just weird the way it was working out that way. So the next header, known as the extension header, there can be a next header in the first extension, and it keeps going until the upper layer flag is seen, which is this guy. So it'll keep going. Like I said, it's not going to actually break it down in steps. It'll if you were to look at Wireshark, it'd be consistently one after the other, but it'll be indented until it gets onto the upper layer protocol, and then it'll start to jump up to the next layer. So that's the idea behind that. Pretty straightforward, but I guess it could be kind of confusing in how it works. Now let's talk about fragmentation and what fragmentation really means. So this, when we get into, let me scroll down to the bottom real quick, move my mouse off to the side here. What you're going to get, fragmentation, fragmentation, and I don't think it's listed in this one. No. We'll talk about that when we get into TCP operations with maximum segment size and TTL and things like that. But, and the MTU. The MTU, fragmentation, and the MSS, the maximum segment size, these three features, options, I guess it would be, or I'm trying to think of a good word to use for them. Terms, we'll just go with that for the moment. These three terms are used pretty much in conjunction with one another. One has definitely the potential to offset another one. So if you are trying to send traffic to figure out what the MTU of a path, and we'll talk about path MTU here in an upcoming video. If you're trying to determine the path MTU from point A to point B, and you're going over several different types of media, maybe you're going Ethernet to fiber, back to serial, back to Ethernet, down to fiber, and then you're done, depending on how things are working. The MTU may be set, and if you have the do not fragment bit put in place, when that packet hits a certain router in the transit to the destination, if he detects that the MTU is too big, is too small, and the packet needs to be fragmented in order to be continued to forward, he'll send a message back to the sender to manipulate the size of the MTU down to a small enough MTU to fit through the lowest MTU connection from point A to point B. So basically what it's saying is it's a way for you to determine what the best MTU size is for a particular segment along the line. It's almost like EIGRP picks the slowest bandwidth in the network and uses it as its bandwidth metric. So if it's a serial connection, it's going to default to 1544 for T1. That's just one indication. So now the actual definition of it is when a router receives a packet, it examines the destination address and determines the outgoing interface, and to use in that interface's MTU. If the packet size is bigger than the MTU and the do not fragment bit in the IP header is set to 0, the router may fragment the packet. The router divides the packet into segments. The max size of each segment is the MTU minus the IP header. So 20 bytes minimum, 60 bytes maximum, which we just talked about. So the router puts each segment into its own packet, each fragment packet having the following changes. The total length field is the segment size. The more fragments flag is set for all segments except the last one, which is set to 0. The frame offset field is set based on the offset of the segment in the original data payload. This is measured in units of 8 byte blocks. The header checksum is recomputed. So, for example, for an MTU of 1500 bytes and a header size of 20 bytes, the fragment offsets would be multiples of 1500 minus 20, which is going to be 1480, divided by 8 equals 185. These multiples are 0, 185, 370, 555, 740, etc. It is possible for a packet to be fragmented at one router and for the fragments to be fragmented at another one. So you can continuously fragment down the line. For example, consider a packet with a data size of 4500 bytes, no options, and a header size of 20 bytes. So the packet size is 4520 with the header built into it. Assume the packet travels over a link with an MTU of 2500 bytes. Then it will become two fragments, one of 2500 and the other one of 2040. So note that the fragments preserve the data size, so it's 4500 total. So note how we get the offsets from the data size. So 0 and so on. You guys can read this So we come down a little farther here, and it says fragment 1 1500, 2 is 1020, fragment 3 is 1500, and then we come down to 560. The header size is the same, the data bytes are all below 1500, and the more fragments flag is tripped. So note that the fragments preserved, etc. Note how we get the offsets from the data offset. So they break them down as such. So we can use the last offset and the last data size to calculate the total size of the data. So 495 times 8 plus 540 equals 3096, or 3960 plus 540, which is 4500. So long story short, the router will keep computing this until it gets from point A to point B, and then it will be able to reassemble this when it gets to the destination. It's a lot of detail, and I think it's good to know because they might go this deep inside of the written exam. They might, but chances are they won't. So just in case they do, it's good to know how the router actually does it from a higher level point of view. So now, inside of the IPv4 header, they do have the DF bit, which is a do not fragment bit. What will end up happening is if the do not fragment bit is triggered, so it's turned on, that's a 1 in the IP header, and this hits a router on the incoming interface. If he can't fragment, or if he has to go through the router, what'll end up, he'll send a response back to the sender. I can't do this. This is the MTU that it has to be set to in order for me to forward it. Now, IPv6, on the other hand, doesn't do that. And we'll look at that right now. A packet containing a fragment of an original larger packet consists of two parts. The unfragmentable part of the original packet, which is the same for all fragments, and a piece of the fragmentable part of the original packet identified by a fragment offset. So what ends up happening is, with IPv6, is you're going to have a too big flag tripped. This is supposed to be my attempt at a flag. And what will end up happening is that'll be sent back just like this. And what will end up happening is the sender will have to readjust the size and send it down, modify the MTU to fit this hop's or this router's forwarding capability, if that makes sense. So that's the idea behind that. So let's talk about TTL and MTU before we wrap this up. So TTL is the time to live value. So time to live is an 8-bit field, as you can see, 255 maximum. So what does that mean? I mean, and I'm kind of giving you a wink, wink, ha-ha, nudge, nudge. Basically what that means is the most routers that a single IP packet can traverse is 254. Why do you say 254? Well, simple. If you say, I'm not going to draw 254 routers, but let's say, for instance, you go router 1 sends to router 2, and then you've got ... you've got router here and a router here. So we got 1, 2, 2, 5, 3, or I'm sorry, 4, 2, 5, 5. Hits this guy, he's going to be leaving here at 255, he's going to show up here at 255, or 255, and this guy's going to subtract 1, which is going to go 254. He goes through the network until he hits this guy. At this point, he's going to have 2 left, and he's going to decrement 1, and then when he gets to this guy, he's going to be at 1, and therefore he's going to die. Skull and crossbones. He's dead. That's my horrible attempt at skull and crossbones. He's going to die at that limit. This is to prevent packets from looping indefinitely inside of the network. So I'm going to keep going until I decide to stop. So if this continues to happen, what's going to end up happening basically is he's going to keep going back and forth, and this could potentially happen in a real production environment. I've seen it happen. It's usually if you do a trace route to a destination IP, and this is supposed to be a D, by the way, destination IP. If you do this, the router is going to show you up to 30 hops. Well, that's 225 less than the maximum. So I guessing you're seeing the point of this. 255 hops is the most an IP packet can handle, because every router that the packet traverses or goes through, that router takes one hop off of the of what it's got left in the TTL value. Pretty simple. So that's what TTL is. So no packet is immortal, is basically the line to that. Then we have MTU, everybody's favorite topic of the day. So MTU, as we've already discussed when it comes to this, is how big of a packet you can send to a destination. So, as we already discussed this, and I'm not going to go into too much more detail because of the fact that I already went over this in kind of a lot of detail. MTU is going to be how big of a packet can be sent from point A to point B. Now, MTU for some is 1500, some for others it's 4932, I believe, is for FDDI. 4352. So Ethernet is 1500 bytes, FDDI is 4352. PDU, or the Protocol Datagram Unit. Fragmentation occurs when going from a larger MTU media to a lower MTU media. Jumbo frames allow for MTUs that are larger than 1500. New services require encapsulation in the frame. What? Well, basically what this means is the more features you want to implement in your network, and the more services that you want to have interacting with other services. This is, at the end of the day, we're going to say we have a payload here. This is going to be our payload, so we're going to say payload. This is our payload. What's going to end up happening is you're going to have all these headers, all this extension, all this encapsulation, and so we have all this stuff going on in the front. I'm going to keep going for just a moment. What this basically means is for every additional service and every additional layer that this guy has to go through, every one of these is going to get filled with something. It may not use all of these particular headers or all of this particular encapsulation, but let's say, for instance, you're sending it over, this is going to a TCP connection, and this is going over GRE. Maybe it's going over a MPLS circuit, and let's say that there is several labels, and you have, 8 or 10 labels inside of that. This is all encapsulation that's got to be taken up. Then we hit, maybe it's going to over an OTB tunnel. Maybe it's going between two data centers, so we're going to have that encapsulation. So for every type of technology that is a packet is going to have to traverse and be encapsulated inside of another technology in order to reach that packet, and depending on what it's got going on in here. So maybe it's web and voice over IP, because maybe you're using a phone and daisy chaining a computer to it. Okay, so we have a phone and a PC. So for every bit of encapsulation that has to be added to the packet in order for it to get from point A to point B, that's all encapsulation. This is all bits that are going to be taking up space inside of the packet to be encapsulated, and these are all headers. Could be, like I said, it could be TCP as the type of connection. It could be going over GRE. It could be encapsulated inside of a VPN tunnel, so there could be IPsec here. It could be going over a MPLS L3 VPN, so we're going to have MPLS encapsulation in there. Then there could be, some QoS markings that are inside of this guy, and the experimental bits are turned on. So this is going to be more. I guess you can see where I'm going with this. There's more and more encapsulation with the more and more services you throw at it. So some are going to be transport encapsulations like GRE, IPsec, MPLS, things like that. Other ones could be services where you've got Citrix and web and all this other stuff that goes on into play. It depends on what you've got running. So the more you have playing, the more you're going to have going on. So just be aware of that when you're trying to figure out your networks, and whether you want to go with 10-100 ports or if you want to go with 10-100 1000 ports. I know a lot of places, and this is kind of going off the idea of MTU, but I know a lot of places that are actually doing a lot of, they're getting rid of the old chassis boxes, so the 4500s, the 6500s, they're getting rid of these guys, and they're putting in stack-capable devices. Which stack-capable device is real simple. It's just any other one-use switch, whether it's a 3560 or 3750, or that's a 3 there, 2960. It doesn't really make a difference what model switch it is. What they're doing is they're actually stacking these guys together, and for redundancy. And what ends up happening is these guys right here are going to be running gig on all of their ports, and let's say this guy right here and this guy right here have uplinks to another switch, and these are 10 gig fiber channel connections. Maybe this guy is going off to a fiber switch with SAN, or maybe this guy right here is doing whatever. He's going up to a server with 10 gig uplinks, or whatever the case may be. So you have the uplink capability. The idea now is you have all this extra bandwidth to work with. The more bandwidth you have to work with, in most cases, that's going to be less MTU that you have to worry about. Because the fact of, when it comes to these larger bandwidth connections, that will give you the capability of using jumbo frames. Jumbo frames are going to become a big factor in your networks. Now, fast Ethernet, because the fact that its maximum speed is 100 megabits per second, has a MTU of 1500. Gigabit Ethernet, Gig-E, can go above that. Okay, 9216 is its maximum MTU. Okay, now because the fact that we're still going to be using 802.3 as our IEEE, that's my attempt of IEEE, is going to be the standard that Ethernet follows, there's still going to be some hindrances for that. Now, if you're going to use Cat 6, that's been changed a little bit. It's a little bit different than Cat 5e. Now, Cat 5e has a limit; it can only go up to gig. Cat 6 can do beyond gig. I believe I've seen 10 gig running on Cat 6. Could be wrong, but at least that's what I think I saw running. So depending on what's going on, all of these play into how you're going to design your network. So knowing what capabilities you have for your network is going to be kind of crucial. Now, going back over here to the chassis boxes and stuff like that, and having your supervisor modules and things like that, the more bandwidth you have to play with, that's going to affect your MTU. That's the basic line to it. So at the end of the day, just be aware of what's out there and what you want to work with, because depending on what you want to work with and depending on what there's capabilities of running with will determine how you actually implement your network. So I hope this has been informative for you. I would thank you for viewing.